Hello, everybody. My name is Catalina Garcia, and this is my presentation on neural communication and specifically action potentials. This is for the Bio 510 class. So neural communication. This information is from our textbook as well as this image. Neural communication is accomplished by nerve cells or neurons. Here, and I believe you can see my mouse, here we have a picture of a neuron as well as a quick breakdown of neural communication. Our specific communication we will be talking about are action potentials, which occur through electrical signals that are caused by rapid fluctuations of the membrane potentials. We will go into that further on the next couple of slides, but here focusing in on this picture, we have zone 1, which is the input zone. Here is where incoming signals from other neurons are being receptive. As you can see here, these dendrites are receiving the signals. Just a quick layout, we have the nucleus, the cell body, and then the dendrites labeled here. But here is this first zone. Then we have the trigger zone, which is the axon hillock. This is where the action potential is propagated, where it is initiated. And then, so it is initiated here at the axon hillock, and then it travels down the axon, and we go into 3, the conducting zone. This is where the action potential is being transmitted and where all of the chemical membrane potentials are fluctuating, and we'll see that in another picture and a graph coming up. But here, so the axon hillock is where the action potential is generated. It travels along the axon, and then it ends here at the axon terminal, which then sparks another axon as it does travel from axon to, it sparks another neuron as it travels from neuron to neuron. So 4 here, just really quick, this is the output zone, releases a neurotransmitter that influences other cells. So whether this be connected to a muscle or to another neuron to continue the connection, this is where it happens. So from axon hillock along the axon to the axon terminal. Continuing on, we have our action potential. We will be explaining it through this graph. As stated here, action potentials are fluctuations of membrane potential. So it is the depolarization and repolarization of the membrane. They are brief, rapid changes in membrane potentials used by neurons. As we stated earlier, they are initiated at the axon hillock along the axon to the axon terminal. So from this graph, okay, going on that you can see my mouse, we have the resting state of the cell at around -70 millivolts. Now for this resting state to go to threshold, which is about right here at this green line, as you can see, threshold potential, there needs to be a stimulus that carries enough millivolts that it raises the negativity, decreases the negativity from -70 to -50. And this is important because at resting state, no action potential is being sent. And then for stimulus to come to increase the positivity in the cell, get it to threshold level, this is where an action potential can start being sent. It occurs first at threshold where depolarization happens. At depolarization, there are voltage-gated sodium ion channels that are opened, which causes an influx of sodium ions. This depolarizes the cell. So first it was polarized, it is stable at this -70 millivolts, stimulus occurs. Then we get to threshold level where these voltage-gated sodium ion channels are open, depolarizing the cell. We get to an overpolarization area here that's not labeled, but it's around +30 millivolts. And then we move into the repolarization phase. The purpose of the repolarization phase is to get the membrane potential back to resting potential. So repolarization causes, at this step is where the voltage-gated potassium ion channels open. So at overpolarization here, the sodium channels have closed. Then we have the potassium channels opening, which causes the repolarization. But for repolarization to lead to resting potential, it first must go through hyperpolarization. So the action potential is this red section here, the depolarization of open sodium channels, they close at overpolarization here, and then potassium channels open, and that's the action potential. So it has been sent along the axon, but this portion of the axon still needs to go back to resting potential. It first leads into hyperpolarization, as some of these potassium channels are still open as the membrane is reconfiguring, going back to resting. And so this causes the membrane potential to go past resting state to around -80 in this hyperpolarization state. Also here is the refractory period. So during this time where the cell is reconfiguring and the membrane potential is going back to resting, the cell cannot send another action potential. And so this is considered the refractory period, where the cell can no longer send one until it gets back to resting potential and the process can start over. So that is the refractory period. And then repolarization leads into hyperpolarization, which results in the membrane going back to resting potential, now ready for another action potential to be sent. And so this occurs at one portion here. It occurs at one portion here and then moves along the axon and it just keeps being sent, and it's not diminished. It just travels along the axon until it gets to the terminal, which will then either be inputted to a muscle or to another neuron. So continuing. This is another view of what is happening, what I just explained. So here we can see the cell body, the nucleus, the dendrites, and here would be the axon hillock. This is just a different visual representation of what I just stated. So here you can see the active area, peak of action potential, so the axon hillock. Here you can actually see the sodium channels. At depolarization is when sodium channels are opened. And so you see this influx of sodium ions causing the depolarization. Then we move on to here. This area is inactive and it is getting ready to receive its threshold being met so that it can do what's happening here. And then here, the rest of the axon is just waiting because it's still at resting potential. As I said earlier, it's traveling, so it's just waiting to happen. So you can see here the direction of propagation is going this way. At repolarization, as I stated, the sodium channels are closed, so you see they're not open here. But at this portion, the potassium ion channels have opened, and this causes an efflux of potassium ions. So this potassium is leaving, which is repolarizing the cell. As you can see here, there's the negativity of the cell is being disrupted, it's being depolarized, and then here it's being repolarized as the resting potential is being achieved. It's going back to its resting state. So as it says here, excuse me, previous active area returning to resting potential, no longer active. It is in its refractory period, as we stated earlier. It cannot receive another action potential. It needs to get back to resting period. And so now you see the next portion of the axon is it received threshold and is now going through this first step that we saw here. So you can see how it's traveling. So it was here, and then it's here, and then now this portion of the axon is going through repolarization and is going back to resting state. And you can even see here, I was explaining it through the millivolt graph, and this is showing the a reflection of what's happening on that graph versus what is happening in the actual neuron. And so you see that it'll just keep traveling down, down, down until it gets to the axon terminal. So let's see. Okay. So back to this, we see just a clarification that the repolarization's purpose is to get back to resting potential, but here the depolarization and repolarization is the action potential. But as you see here, it doesn't just happen and then, the action potential isn't just set. It's not just depolarized and then repolarized and then the cell's ready to go. It actually has to go into that refractory period so that the propagation is moving forward. This is so that it's amazing. The refractory period makes sure that the potential never moves backward, but continues going forward. So as stimulus or another neuron generates the action potential here, we know that it will move forward. And so this is what ensures that action potentials are good for long distance, as the action potential does not diminish because it has to travel along here, but actually keeps its impulse and travels along, so it is good for long distance. Action potentials require these sodium voltage gated channels, and they are voltage gated, meaning that the threshold needs to be met. So as we saw here, voltage gated channels, so voltage meaning millivolts. This at threshold is when the voltage gated sodium channels are open, so the threshold needs to be met for them to be open. Here at overpolarization, that is not marked here, but here is when those channels close, because the voltage necessary for them to open is no longer there as it is being depolarized, so they close. And then it's same here with repolarization and the potassium channels. So speaking on that, in research, we see that there is a necessary greater density of these sodium channels in the axon hillock region. So from Cole et al. 2008, Wistar rats were used by these authors to support the assumption that a high density of sodium channels are necessary at the AIS, which is around the axon hillock, where action potentials are meant to be sent. So specifically, there is a higher density of these channels at the AIS compared to the soma and proximal dendrites. So at this portion, there is an increased amount of sodium channels. So these Wistar, that's the name of the rats, these Wistar rats were used to support the common assumption that there's a high density of these sodium channels needed at the axon initial segment, which is what the AIS is. I will be saying AIS from here. So these axon initial segment. So further, the Wistar rats were used by the authors to support this assumption. That is the purpose of their research, to support the assumption that there is a higher density at the AIS of these sodium channels compared to soma and dendrites. So dendrites, and then here we have the AIS. Sagittal brain slices of the somatosensory cortex from these rats were taken and then used for various testing. The testing procedures used were patch clamp testing, whole voltage clamp testing, sodium imaging studies, as well as immunocytochemistry. So here in our first chart, we have an overlaid space voltage plots and simulations in which the AIS sodium channel density was increased from 500 to 5,000. So this is just a visual representation of what I was saying. Here in part B, we see, table B, site of action potential initiation, which is the distance from axon hillock, versus the AIS sodium channel density. Again, these are just visual representations of the research. Continuing on, also, we have in this table the morphology of the model neuron with dendritic recording location indicated. And so that was here. So this is the neuron we see. And then here we see, and then here we see examples of action potentials recorded in the apical dendrite from the soma in the models with indicated AIS sodium channel densities. So, go back. Researchers, the patch clamp testing showed only a slightly higher density of sodium channels, which was contradicted from the other 3 tests. So I stated 4 tests earlier, and the first test actually showed only a slight difference in density, while the last 3 tests showed significant density differences. The authors had concluded what happened was that this paradox was because the sodium channels at the AIS were anchored. So this did not allow for channels to be drawn into the pipette for recording, which then resulted in inaccurate readings. So the authors retested the patch clamp test by disrupting the foundations of these sodium channels, and then were able to get the results that were conclusive with the other testing. The authors concluded that the density of sodium channels at the AIS is around 50 times that recorded from the soma and proximal dendrites. So that's very interesting that it would have this, that they went in using Wistar rats to support the thought that there is an increase in sodium channels at the AIS, and then found that it is actually 50 times more than recorded at the AIS compared to the soma and proximal dendrites. So they were able to conclude what they wanted to conclude. They were able to find this. So that was action potentials and research. Action potentials involve only a small portion of the total excitable cell membrane. They are propagated, they're conducted, as we saw earlier. They are propagated here. They move along the axon to the axon terminal. We know that the strength of the signal does not diminish because of their travel, and so they are used for long distance. They're great for long distance signaling. And research, we can see that they are being studied for the density of channels, these voltage-gated ion channels that are very necessary in their completion of sending stimulus. So that is action potentials. Here are my references. That is action potentials, my presentation on this aspect of neural communication. Thank you very much. My name is Catalina Garcia. Thank you.